Buckling of thin-walled open section. Generally, there are two types of steel structures: the hot-rolled section as well as the cold-formed section. As you know, the hot-rolled sections are made at a temperature of 1700 degrees Celsius, and the cold-formed sections are generally a steel sheet, strip, plate, or flat bar, and they are made by forming, basically roll forming or press breaking operations at room temperature. They are also known as thin walled sections as well as the light gauge section. The thickness of cold form steel, it ranges from zero point 0.4 mm to 6.4 mm. Here in this lecture, we are focusing more on the different buckling modes of thin walled open sections. As in the screen, you can see a lot of cold formed sections are possible. Generally, they are classified into open section as well as closed section. In open section, there are symmetric, like doubly symmetric, monosymmetric sections are there, and we have the cross sections. So the highlighted one is the channel section. You can see a channel with lips. Then you have the EZ sections, back-to-back channel sections. All those structures are practically possible by cold forming. There are some typical cold formed steel sections which are possible and used for making the definite or desired structural steel shapes for roofs and other beam purposes. They are the lipped angle, lipped channel, Z, sigma, hat, etc. Coming to the design and behavior of the cold form steel structures, the main challenge of cold form steel are they are very highly susceptible to local buckling. We have we can divide the cold formed steel shape into stiffened and unstiffened elements. The stiffened element are supported along both its longitudinal edge, and the unstiffened element they are supported along one edge only, with other parallel edge being free to displace. So, so have a channel section here. So for this channel section, this web element is stiffened element, and these both the flange elements are unstiffened. To make this flange element stiffened, we can provide the lips. And there are multiple or intermittently stiffened element. They are made of very wide thin element divided into two or more narrow sub elements by the introduction of intermediate stiffness. Say, due to the practical reasons, this web height is very high. Then you can stiffen this web by providing an additional stiffener like this. So you'll be having a shape like this, and this will additionally stiffen the web member. So how to get the maximum stiffened elements? So you have a channel section. To stiffen it, you can provide the lips as shown here. Then you can again stiffen by providing additional length for the lips, and this is an example of the the multiple stiffened. The different failure modes in thin wall sections, it include the Euler buckling, which is the normal column buckling, then some special buckling like the flexural buckling, torsional buckling, flexural torsional buckling, and these are applicable for majority of the column structures. And we have special type of buckling like the local buckling and the social buckling, which is applicable only for the colform steel members. So the flexural buckling, here the bending is happening about the principal axis, and in the case of torsional buckling, the twisting is about the shear center, and for torsional flexural buckling, the bending and twisting will happen simultaneously for the member. These are the figures showing different local buckling, distortional buckling, and flexural torsional buckling. So you can see in the figure that in the case of local buckling, the overall geometry of the cross section is maintained, and the local buckling will happen only between the edges. In the case of distortional buckling, the shape even gets changed on comparing with the local buckling. So actually, this figure it corresponds to the local buckling, and in the case of distortional buckling, there will be a transformation of the flange like this, so that the overall geometry is lost in the case of distortional buckling. And the next one is the flexural torsional buckling, which we will see in detail in the following slide. Coming to the local buckling, if individual part or plate elements buckle without overall buckling of the member, it is known as the local buckling or local instability. As we discussed for channel section, the overall shape is maintained and there may be buckling only in the web for this case. Here the width or thickness ratio of each part gives the centerness ratio of the element, and these ratios will control the local instability. It should never be allowed to never be allowed before overall buckling of the structure except in few cases of a web of plate corridor. So plate corridor is a different design concept in which the local buckling is also accounted for taking the post buckling strength for designing the plate corridors. So most of structures except the plate corridors, local buckling is considered as to be a indication of failure. And next we have the flange local buckling. You can see here the flange is getting distorted. If the width over thickness ratio of the compression flange is greater than a certain limit, flange can buckle locally. This is known as the flange local buckling. And the figure shows the web local buckling in which the web is buckling and the flanges remain straight. If depth over thickness ratio of the web is greater than of certain limits, that is, if the web is too slender, then the possibility of buckling will happen in the webs. The web local buckling occurs in a diagonal position and it is produced by the diagonal compression existing in the web due to shear. The web crippling occurs due to the local compression transferred by the flange to the connecting portions of the web. So we are to summarize the different failures in colform steel sections include local buckling, in which the longitudinal axis of the member remains unchanged. The cross-section deformation occurs due to the bending of the member's inner walls and buckles before the full strength of the member is attained. In the case of distortional buckling, it is also called as stiffener buckling or local torsional buckling, in which the rotation of the flange at the flange or web junction in members with the edge stiffen element. So you can see here the cross section is getting deformed. In the case of global buckling is a buckling mode where the member deforms with no information in its cross-sectional shape. That is, you have a column like this, and this column will bend like as a single column. It means there won't be any deformation for the at the cross-section level. This will be as initial as the column. So there won't be any deformation for the cross-section level. Only the entire column will buckle as a beam. And web crippling is simply the bending of the plate when it's too thin to carry the plate bend. So you can see here the web got buckled. Next comes the important title is the flexural torsional buckling. This type of failure is caused by the combination of flexural buckling and torsional buckling. This type of failure can occur only with unsymmetrical cross sections with one axis of symmetry, single symmetrical shape. So we'll see in detail in the coming slide. The flexural torsional buckling. For singly symmetrical shapes, align the cross section of the member such that you can see here an angle section, sorry, a channel section, which is actually symmetric about the y-axis and unsymmetric about x-axis. So the y-axis is the axis of symmetry and x-axis is the axis of no symmetry. The x-axis is subjected to flexural buckling. So about this horizontal axis, the beam will uh, have a flexural buckling. And about the y-axis, it is subjected to two types of buckling. About this axis, it is subject to the bending as well as the torsion as well as the bending. These two actions occur simultaneously. That is why we call this a flexural torsional buckling. Since there are two actions in flexural torsional buckling, then the source of strength will be a combination of the flexural and the torsional actions. So you can see here and pictorial representation of flexural buckling, which happens about the x-axis only pure flexure, and in the case of same channel section about y, you'll be having a flexure plus the torsional buckling.